We continue our discussion on color fundamentals and processing of color images. In the last few lectures, I have discussed how colors could be represented as a trichromatic vectors and how the perceptual factors of color in terms of chromatic experience in terms of hue and saturation could be obtained from the calibrated chart as proposed by an international body of colors, or in acronym CIE. There is a CIE chromaticity chart from where you can represent a color in a XY normalized XY chromaticity space. And as you can see here also in this particular figure, that the colors are shown in a semi elliptic region, and where the peripheral regions peripheral curve is showing different wavelengths. For example, the wavelengths starting from this point is 700 nanometer and this point is 520 nanometer and this point is 380 nanometer. And across this periphery, as you move from from this, if you traverse from this point and come to this point, wavelengths are decreasing in this order, and different wavelengths, they correspond to a particular color, a pure color that is sensed by us when that electromagnetic wave of that wavelength is we receive the energy from those wavelengths. But in the chromaticity space, any color, when they are represented as a superposition of three primary colors, particularly when we capture in terms of red, green and blue, then we can convert those color points into a two-dimensional chromaticity space that we have discussed, that is the XY chromaticity space. So, for example, this is the x axis of that space, this is x axis of that space and this is y axis, and any particular color at this point, it has been shown also that what is the color of that pixel, that is how this visualization has been created, this graphics have been created, where it is also showing the color. So, you can see there are large regions of having almost similar color sensation, and the minimum the region where colors are almost indistinguishable, they can be approximated by ellipses. As you can see, one example of this ellipse is shown here, a larger ellipse is here in this region. You can see this ellipse, I am drawing it just for your convenience. So, centering this point, all the color covered by this point, all the chromatic point, they will generate the same sensation. Now, these ellipses are known as McAdam ellipses, and these ellipses are also called just noticeable differences in color ellipses, or JND ellipses. This is a very common acronym what is used. So, if your points within these JND ellipses, so all the perceptual the perception of color would be almost similar for in our human visual system. Now, the problem here in this XY XY space is that the size of this ellipse is non-uniform. You can see the size of this ellipse at this location is quite large, whereas near to the red region, this size is quite small. Very small ellipses are shown here. So, so that is a problem with representation of color in an XY chromaticity space. So, there is a proposition, another proposition for another color space, where you can make this ellipse, size of this ellipse is more or less uniform. It will not be exactly uniform in every places, but we try to minimize the variations of these sizes, and this color space is called uniform color space. The uniformity the uniform, that adjective comes from that point of view, that the sizes are trying to be, we are trying to make those sizes uniform by making some transformation on those x y points itself. So, this is one example of this transformation. So, you can see that, just to make it clear, let me rub these points. So, you can see that the transformation I have displayed here. So, this space is called u prime v prime or u v in short, that is the uniform color space. Again, it is a chromaticity space of representing only the chromatic components, and the kind of transformation from the x y z coordinates of the color, representation of the color has been shown here. So, the point to note here that it is a projective transformation of x y to make the ellipses more uniform. Say you consider this diagram, here you can see that the differences of sizes of ellipses in this zone, and which corresponds to the green zone in this space, and in the red zones or in the blue zones, they are they are reduced remarkably. So, this space is more suitable when we are trying to compare colors in terms of defining certain distances, though it is ellipse, it is not circle. So, Euclidean distance is not very appropriate in that sense in this space, but still you can consider the neighborhoods or sizes are almost at least sizes are similar. So, they would be more appropriate, or they would be more effective for distinguishing colors when they are represented in this space. So, let us continue this discussion on color representation. Let us see what other spaces are there. So, one of the, with respect to the discrimination of colors, there is another very effective space that is proposed also by the international color body CIE, and this space is called LAB space, or we define this space also L star S star B space. Here the distances would be more effective, Euclidean distance would be more effective, as the distinguishable the ellipses, if I convert in the AB space, or that is AB chromatic space. So, those will be more circular in that shape. So, in this space we have one luminance channel and the two color channels A and B. I am referring them A and B, though sometimes they are shown also A star, B star. As a transformation is also shown here, you can see the transformation in this part. So, we have L star, S star, B star, and you can see that is a nonlinear transformation which is made using, once again they are made using XYZ representation of the color. And note that all these XYZ values, they are normalized by their by the respective values of reference white. So, for example, reference white is represented as Xn, Yn, Zn. Usually the white is that white color, and we know that corresponds to the chromatic, in the chromaticity chart of XY chromaticity chart, the point is nearly 1 by 3, 1 by 3 in the XY coordinate. Almost all the components of XYZ would be equal, but they may not be exactly equal. So, this is a kind of calibration you need to do with respect to your system. So, find out the white, what is the definition of white in your system, and it is a kind of white balancing operations in the color representation. So, once you get these values, and then you can normalize XYZ coordinates as x by xn, y by yn, and z by zn, and then again use these functions to derive L star, S star, B star. And so, in this model, the color differences which we perceive, it correspond to Euclidean distances in CIE lab. So, it is very effective, and the problem of distinguishing even in the uniform color space, that becomes much reduced. I mean, we can mitigate that problem to a great extent if we use L star, S star, B star for this purpose. Just note that the A axis in this case, it extends from, it is shown in the figure also. So, this is the A axis, this is the negative part, this is the negative direction, and this is the positive direction. So, minus A is green. So, this is a green portion, this is a red. Similarly, for B axis, this is a positive B, and no, this is actually luminance. So, positive B is showing here, and this is a negative B. So, this is yellow, this part, this is a yellow, and this one is blue. So, blue to yellow and green to red, that is a kind of variation of hue in this space along this axis, principal axis, and along the L axis, which is shown here as a vertical line, it is the intensity what is being varying along that axis. There is another color space which is called YIQ color space, and its respective transformation has been shown here. It is a linear transformation. It has the property of better compressibility of information. So, usually the chromatic component of I and Q, they require less bandwidth to represent the color variations. So, if you consider any video signal, color video signal, and if the color is represented into these three forms other than convert them from RGB to this form, then the component of I and Q in that signal will require less bandwidth. In fact, that is why this particular conversion is used in television signaling, color television signaling, where this conversion has been made, and we can also use in the digital television signals. So, it is a luminance of Y is encoded using more bits, because it requires more bandwidth, whereas the chrominance values I and Q, they require less bit. So, the idea is that humans are more sensitive to the intensity Y, and in fact, if you have black and white television signal, then you can just simply use the Y, and there is a signaling encoding, so that even the encoding of I and Q will not affect the receiver of black and white TV, but that is a different point which we are not going to elaborate here. So, the fact is that luminance is used by these black and white TVs, and all three values are used by colored TV. So, this YIQ is also a very good model for sending information as IN by factorizing information into these three channels. The space YCB Sear space, we might have already mentioned this space when we discussed about image transformation. Actually, this is the space, this is the color space used for image compression in JPEG standard and in many other standards, subsequent standards, also video standards. So, you can see the transformation here. There is a linear part of it, and then there is a translatory part of it, which makes this transformation as an affine transformation. And just to note that now it is also having a better compression properties, because of that it is used in different compression schemes. And here Y represents the luminance, and CB and Sear they represent chrominance parts. CB is called complementary blue, and Sear is called complementary red. That is the full term. But it is not a linear transform, it is an affine transform, because there is a additive component in the transformation, translatory component or additive component at the end, like this particular component which makes this transformation affine. Otherwise, if I leave aside this part and consider modified CB as CB minus 128 and Sear as Sear minus 128, then you have a linear transformation from RGB to that. So, that is also sometimes used in color representation. So, this particular translation is done with this motivation that these values without this translation it is ranging in the negative zone. So, for the convenience of representation in digital storage and making all those values positive, so that you can represent them in unsigned byte color representation or pixel representation. Assuming if red, green, blue, the values they vary from 0 to 255, you can see the values of CB and Sear after transformation will vary from 0 to 240. So, that is one of the motivations why we make this kind of affine transformation. There are other nonlinear color spaces where again this hue and saturations they could be factorized, they could be factored out from the achromatic informations like intensity. So, this is showing one such example where you can see it is a conical shape representation of a space, and at the the intensity is varying as we move towards this as we move towards the vertical directions, whereas spatially in the horizontal directions you have the direction of saturation, and the hue is represented by the angle in this. So, such a kind of polar representations what has been shown here, and depending upon angle you can see. So, your reference direction is red, and then your as you increase your angle there is a transitions from white, green, cyan, blue, magenta to red, as you can find out in this circle representation or in this hexagonal representation. So, we can elaborate this transformation further, the mathematical form that we will see. So, the interpretation here is that HSV stands for hue, saturation, value, value stands for intensity, and so hue relations are naturally expressed in a circle as I have shown here, and this is these are the expressions how the intensity, which is the value represented here by I, which is just the average of red, green, blue values. And then saturation expression is also very simple. It is 1 minus a fraction of intensity and the minimum value. So, fraction defined as a ratio of minimum of RGB to the intensity value, and it is a 1 minus of that value is saturation. And whereas hue is also expressed as angle as has been interpreted in that space. So, the implications is that HSV model, it is uniform, that is it is equal steps, it gives the same perceived color changes. So, it has that uniform representations of non-distinguishable colors, that kind of neighboring color, non-distinguishable color, that shape also here it is quite uniform, it is a 3-dimensional representation. So, it's, if I say that is a kind of circular ball around a point. So, it has that effect, but though you should note the the region, the conical regions, it is a double conical region what is being represented as it is shown in this part of this diagram, and around this point you take small spheres, spherical neighborhood, and that would be uniform here. And saturation is the distance to the vertical axis, that is 0 to 1, and intensity is the light along the vertex. So, these are all normalized representation. So, ranges of saturation, intensity, and hue is an angle. So, it ranges from 0 to 2 pi. The other interesting color space, it has again a theory of opponent color processes, opponent processing of colors that is going on in our visual system. It is supported by that theory. So, and this space has been proposed. What it does that the theory says that by processing signals from cones and rods in an antagonistic manner. So, they act in an antagonistic manner. So, rods are kind of inhibiting when cones are very active, or rods are active, then cones are inhibiting. So, that is the antagonistic way they act. However, so let us consider the representation, and in the overlapping spectral zone of 3 types of cones that has been considered. We know that 3 types of cones we discussed, that long wavelength zone cones, that is the spectral response. If they respond more to the long wavelengths, that is called L, medium wavelengths called M, and short wavelengths called S. So, L, M and S types of cones are there in our visual system, and it considered the differences between the responses of cones rather than each type of cones individual responses. So, when we sense a color signal, when the received energy in terms of 3 stimulations of red, green, blue in 3 primary forms, it is not red, green, blue directly being processed for the interpretation of the color, rather the differences of red and green and say blue and also red green plot. We will see later on what is the model of this difference in the next slides. So, because of the fact it is supported by this kind of psychovisual phenomena that no, it is hardly there is any perception of reddish green. We cannot talk about reddish green or bluish yellows in our color perception. So, from there this opponent color processing or theories are developed. So, you can see that what kind of representation is there. So, this is a L cone and M cone, S cone, and you see that L and M they are participating in an antagonistic manner with providing you C1 which is R minus G, that is the component. So, green is opposing the red excitations, and S cone it is Y minus B where Y is basically represented by R plus G. So, that is how it is opposing. So, and all the three cones and the rod they participate in producing the brightness value. So, you have now these three factors of brightness, this is the achromatic part, and R minus G and Y minus B as the chromatic part. So, this is how this color has been represented, and mathematically we can model in this fashion. So, we have three opponent channels like red versus green is represented as G minus R, and blue versus yellow is represented as B minus Y, Y is representing yellow, or B minus yellow is represented as a additive composition of red and green or R plus G. And whereas luminance is black versus white, that R plus G plus B by 3, that is the representation. So, this is if you note the that YCB Sear conversion where you consider only the linear part, you will find that this is somewhat following this principle, because you can see this is red, green, blue. So, Y part is representing particularly this luminance which is the weighted average of red, green, blue, whereas the CB complementary blue part you can see it is representing this component, it is the blue, from the blue you are subtracting addition of red and green. So, that is the complementary blue representation, complement blue representation, and Sear this part it is the red. So, red is you are subtracting major component is green, and also some amount of blue is also subtracting in this model. So, we can see that YCB Sear model in fact that proposition also comes they are motivated by this representation of opponent color processing, and that is used heavily in various applications. So, this is what is our, so this CB prime CR prime is represented to show CB minus 128 and CR minus 128 in this slide. So, now we will be discussing about another phenomena which is observed when you perceive color. It is the variation of intensities or environmental illumination, and how do we perceive colors. You can see when we take photographs or when we take images in varying illuminations, the component red, green, blue they widely vary. As you can see the superpositions of those primary colors, they produce different kinds of image colors in the images, though they are of the same scene. For example, in this case this image is taken by a flash light, and this image is taken by a tungsten lamp, and you can see the differences. The interesting property is that as a human being we can adapt this illumination variation. Even we can understand true red with a largely varying illuminations. That means that does not have much effect on our color perception. But when we take the photographs, there is a large variation of this red, green, blue component. So, we will see that how we can address this phenomena while processing, and how actually it affects our understanding of color when we do the processing. So, this is a sum up that lighting conditions of the scene have a large effect on the colors recorded. This is another example that same scene has been captured in different illuminations, different lighting conditions, but when you record these intensity values or record the red, green, blue components, there is a wide variation. but as a human being, no, we do not see much differences. We can adapt to these variations. So that is what knowing just the RGB value is not enough to know everything about the image. That is a challenge when we interpret a color pixel. And the RGB primaries used by different devices are usually different. That is one consideration. So, for scientific work, we need to calibrate the camera and light source, and for multimedia application, this is more difficult to organize. This factor has to be addressed there. So, there exist algorithms for estimating the illumination of color. So, this phenomena is of adaptation of human to perception of color, same color or true color under varying illumination is called color constancy. So, when we try to address this computation, we call that is the computation of color constancy when we try to achieve this objective. Now, to understand once again that how the colors are perceived or colors are produced, what are the components are there when we record the corresponding color signal. Now, we have to consider two types of reflection that is occurring on the object surfaces. So, there are two components of reflected light. One component is diffuse component, and which is the product of spectral power density and the reflectance curve as we have discussed, and the other component is a specular component, and the specular component is just like a reflection by a shining surface. So, you get almost the same color of the illuminant. It is acting, those surface points are acting like a mirror point. So, it is actually providing you the source of the color of the illumination or color of the light source itself. So, when the same light falls on a surface of diffused surface, you get the color of the surface. When the same light falls on a specular surface or get the specular reflection, you get the color of illumination, color of the light source. So, these are the two different kinds of color we perceive from the same scene. So, in a diffuse reflection, as you can see, it has been shown that after reflection, when the incident energy it is diffused, means it is reflected in all possible directions, and this energy with equal energy in an ideal diffuse surface, and you know that that amount of that energy, reflected energy depends upon the angle of incidence, in this case cosine of the angle of incidence, it is proportional to that. Whereas, specular reflection, it is like a mirror like reflection. So, the reflected energy goes to a particular direction, and if your sensors are in those directions, it will it will get those reflected energy. It is a very narrow directions through which the specular reflection takes place, almost following like a Newtonian law of reflection, like a mirror reflections. So, when we record color, record the intensity values or received energy at a point, a weighted sum of these two actually we are recording. So, let us assume this module diffuse plus specular model. So, as I mentioned, it is a kind of a summarization of the things what I described in the previous slides. So, for a specular reflection, you perceive color of the light, you record color of the light on dielectric objects, on metals, you can get this kind of reflection. Whereas, for diffuse reflection, it depends on both illuminant and surface. It is the product of the intensities received from the illuminant and also the reflectance property of the surface, reflection coefficient of the surface. So, the fact what I stated also that human vision is capable of adjusting the perception of color in varying illumination, and this particular phenomena is known as color constancy. So, we would like to compute or we would like to represent the colors in terms of illumination invariance representation of colors. We would like to have this. That is what is the color computation of color constancy. Now, we can observe if we plot the points, these color points in a RGB space, we can observe a kind of structure, a dog-legged structure as in the histogram of the receptor responses. So, in the RGB space or if we just plot these points, in the RGB space, you will find out the histogram of receptor or dog-legged structure in that plot itself. So, you can see here in this picture we are describing the representation of these colors. Consider a diffuse surface, and so all colors produced by this by this diffuse surface. So, this is the diffuse surface. All colors, they would be more or less of having the similar hue. They may vary over at similar hue and saturations. So, their color vector would be similar, but only they could be scaled by intensities amount. So, they will have a kind in the RGB space, they will have a representation of a particular directions. They will lie on a linear segment again connecting the origin. But on top of that, if there is a shiny surface, that is a specular reflection, then these colors will be related to the color of the illuminant. So, this vector would be again related to it will give a directions along this particular surface, and since it is a superposition, so you get a shifted. So, you will find another directions for some values, you will find another points in this space on top of that, and this structure is a kind of dog legs structure. So, you observe this particular structure in our when we plot this color in a RGB space. So, this is what in a patch of diffuse surface, a color multiplied by different scaling constants that we get, and in the specular patch a new color, and as a result you get this dog leg in this diagram. So, now we discuss about computation of color constancy. So, we see that there are three factors of image formations or for producing the sensory information from the energies of the environment, which is reflected from a surface point. So, these factors are what are the objects present in the scene, then the spectral energy of light source, that is the spectral power distribution, and then spectral sensitivity of sensors. So, we can represent this particular thing, as you can see that E lambda is representing the distribution, spectral power distribution, whereas R lambda x is showing you the surface point, object point x, and that is a surface reflectance spectrum, and S lambda is the spectral response of a sensor. So, it is the accumulated response over all the wavelengths over the spectrum that would be the output of from this particular sensor, and that is what is expressed as I x. So, if there are three such different sensors or having three different types of spectral responses, you will have three such components. So, that is how the color is represented. So, it is the same scene captured under different illumination, and the problem of color constancy is that can we transfer colors from one illumination to another. So, this is the problem statement that we need to derive an illumination independent representation of color, and for that what is required? We require to estimate the spectral power density of light source, that is the first thing, and then use that then normalize the colors what you get in your as a response of sensors. You should normalize these colors with respect to the spectral power density of the light sources. So, the factor which will be doing that normalization, that task is known as color correction, and for estimation of spectral power density, you need to compute the 3 vectorial representation of the color of the illuminant. So, there are one method is known as diagonal correction, and so this diagonal correction is given in this form that you suppose you have a target color of your target color is that the color in the color invariant representation, you would like to transfer all the colors as if they are illuminated by this illuminator, which has the color equivalent of representation of RD, GD, BD, and the actual color of the illuminator in the scene or color of the light is given by RS, GS, BS. So, any color what you get, say RGB, any pixel which is obtained due to illumination, how you can transfer, you can modify it so that as if this color would be, same color would be obtained from the illumination of this color vector. So, that is the correction you were going to do. So, first you find out the proportional factor of these this spectral components of or primary components of these color vectors of target illuminator and source illuminator. Also you compute this factor f, it is trying to normalize the intensity values, so that you can have the same intensity value even after modifying, and then your updated color value should be this. So, I should write here updated value, let me put it prime r prime, that is the updated one, which is f k r r, then g k r r, f k g g and f k b b. So, this is how you can perform this kind of color correction. So, let me take a break here, and we will continue this discussion in the next lecture. Thank you very much for your listening.